Hello, my name is Liam Gleason, and this is my Physics 2211 Lab 2. As an overview, first we're going to be covering the purpose, then the basic physics concepts, the tracker software, the computational model, comparing the two, and then reviewing sources of error, and finally the review questions. The purpose of this lab was to observe the motion of an object using tracker to analyze its motion, then create two computational models, one with the drag force and gravity, and one with just the gravity force, and compare the three. Basic physics concepts we used was the velocity update formula, position update formula, and drag formula. The velocity update formula is derived from Newton's second law and allows us to predict the velocity of an object as it travels through its trajectory. The position update formula is derived from the velocity formula, which is change in position over change in time, and allows us to predict the position of the object as it moves through its trajectory. And finally, the drag formula is used to calculate the effect of air resistance on the object as it moves through its trajectory. So this is the software we used to track our system, which was a paper ball, and the surrounding was everything else. And on the right you can see the X position over time and the Y position over time, and on the bottom right you can see a chart of all three. We use this data and input it into the computational model to calculate the velocity update and position update formula, as you will see next. And just a last note, the forces acting on the ball is gravity and air resistance. Now for our computational model, we made the mass the same as the paper ball. The position vector was the same initial position as it was in tracker, and we calculated the velocity vector using the data from tracker as well. We used the second position of x and y and the first position of x and y in time to calculate these two. The time step is the same as it is in tracker as well, 0.033 seconds. Gravity is obviously 9.8 meters per second. And the proportionality constant for the drag force, we had to figure that out through experimentation, basically, whichever provided the most accurate output. And we settled on 0.001. The final time is also the same as tracker, 0.668. To find the force of gravity, it's just the mass of the ball times the gravity, 9.8 meters per second, gravity of Earth, and it's negative because it's going in the negative y direction. The force of drag was actually calculated using the formula from that I showed earlier, and used the magnitude of the ball's velocity squared and the unit vector of the ball's velocity as well in that formula. And B here is just the proportionality constant. And then next we have the velocity update formula right here and the position update formula. And this is all done in a while loop because it's having to be recalculated at every time step. And as you can see, this is where the time step is added up. And then finally, it's outputted into vectors just to show you what it looks like in the program. And yeah. And to basically, this is the computational model that has gravity and force drag. And for the equation, or for the computational model that just had force of gravity, I just deleted plus force drag right here. So it only, FNet is only comprised of force gravity. Now here we have a comparison of the three. In blue we have the tracker data, which is height in meters over time. In orange is the computational model with gravity and drag, and in green is a computational model with just gravity. As you can see, the computational model with gravity and drag is lower, which completely makes sense since there's an extra force of drag on the paper ball, it will not travel as high. And the tracker data is the highest of all three, which doesn't necessarily make the most sense, but this could be due to human error, as I will state next. Sources of error, firstly, could be incorrect tracker calibration. If I go back, you can see that a meter stick was used to calibrate the tracker software, but due to the angle of the video, it's aiming down slightly. This could be a little off, and that can also explain why in the data the tracker is higher than the other two, when in reality, due to the forces acting on it, it should be lower. The second source of error is incorrect drag coefficient. As I told you, we calculated this drag coefficient using experimentation. Basically just trying different numbers and seeing what they look like in the output. So we could have used a incorrect proportionality constant for the drag force. And thirdly is computational simplification. Obviously, the computational model doesn't account for every force possible that can be acting on the paper ball, so this could also contribute to error. And finally, the review questions. Is terminal velocity represented in either the tracker or the computational models? And the answer to that is no. Neither the tracker, simulation, or the computational model show terminal velocity, and this is because during projectile trajectory, the object does not experience zero net force. A similar experiment to show terminal velocity would be an object falling straight down for a period of time. And secondly, if the object was thrown straight up, would it take longer, shorter, or same time to reach the ground? And my answer is it would hit the ground in a shorter amount of time, as the object would only have the y component of direction, while the projectile motion has x and y, therefore it must travel a greater distance to hit the ground. Greater distance equals greater time. And that's all. Thank you.